in my playlist as well. So it's there in both places and people don't have to look around, I guess.
I mean, of the video or of the document?
Of the video, The documents, I'll post all of these things on Moodle, all the things I have. In my playlist as well. So it's there in both. Huh? Hello? I couldn't hear. Hello?
Yeah, I guess someone said something.
Do
you want me to record or shall I make you co-host and you will record?
No. You've started the recording, right? So that's
okay. No, I only put it on live streams. If I
that'll also record automatically on YouTube, I think so.
Yeah, but additionally, if you want to record, you can record.
Yeah, no. I mean, I'm just thinking out loud as to yeah. So I'll just start screen sharing if you give me Okay, so I guess before I just go deep into FramaC, there was there was an idea of this counterexample to Pliny iteration, right?
No, that's right. So maybe you could do that. I don't know if anybody, I discussed it, and that is something that yes. And also there was, I don't know, Harsh is not here. Maybe that can be done later on. He had some example of CBMC, but maybe we can discuss that later. But please do go ahead. And then, so I had mentioned about this in the class on Tuesday. This is an example of a monotonic function on reals that is not continuous, and also is a counterexample to Plini's theorem, which claims that this iterative application of a collector, like collecting function, starting from bottom, yields least fixed point of that function of an ascending chain. So Diganta has an example. If you want to add if you have thought about it, you're more than welcome to do.
Yeah, so I guess I'll ask that first. Does anyone have any sort of ideas? Because this is one hint, I guess, could be that things are very close to real analysis. Like this idea of continuity is the same as real analytic idea of continuity. So yeah, so I think someone was saying something, right? Hello? Hello? Am I still audible?
Yeah.
Audible.
Yeah. Sure. Okay.
I guess,
yeah. So basically just think about real-to-real functions, and you should be able to come up with a lot of examples. I came up with one example when I was discussing with Sir sometime back before his thing. And then after that, I had thought a little bit more, and I have come up with another example. So I'll show both. So first one is kind of contrived, but basically the idea is you have some sequence, or let's not use X, I guess, any sequence like this, it will work. And I'll show you a concrete example. So you have some sequence, say, approaching 1, right? And then you take your lattice to be this sequence, like elements of the sequence. You also take 1 and you take something else. Let's say that you take 2, and let's say that all of your an is less than 1, right? So it approaches once from the left side. So your picture looks something like this. You've got 1 and 2 over here, and you've got some sequence approaching 1 like this, right? Now, basically what we can do is we can just define f like this. We say that f of an is going to be it's going to be just an plus 1, right? And f of 1 is going to be 2, and f of 2 is also going to be 2, right? So basically this will look in our picture, it will look like f is going to go like this. This one will go here. This one will.
You're considering only the positive reals, no, or non-negative reals.
Yeah. In fact, we're considering a very small part of reals.
Yes.
So yeah, this is our lattice. By the way, this is a complete lattice. That is clear, right? So this is the lattice. Does anyone?
The elements,
yeah. It's clear for everyone, right? That it is a complete lattice and so on. Okay, I'll take that.
So what is the bottom? Here, anybody?
You can take it to be 0.
Yeah, sure, you can, but like we have had some specific an over here. So it's basically a0 actually, it's the bottom, right? This one, this point can be, this one is a0. So this is the bottom over here, right? Does it make sense?
Yeah.
I mean, yeah, you can also like, there's nothing stopping you from adding in 0 and this example will still work. But just the way I've defined it is like, it's a0, which is whatever you've set your sequence to. And you can, 0 might be the starting point for your sequence. Right, but the basic idea is that your function here is basically slowly approaching 1, but then at 1 it just jumps to 2, right? So notice that this function is actually like, you can, this lattice is a subset of the reals and it forms your in some sense a metric space on that, and you can define a sense of continuity in that analytic sense. So in that sense, this function is not continuous, right? So this is not, let's say, and it's also not continuous in the sense of like the fixed points and limit sense, essentially, because this an sequence f of this thing is 1, while I mean, yeah, f of this thing is 2 because this thing is 1. But if you look at this thing, this is actually 1, right? So these two things are not equal. And
It should be the other symbol, right?
Yeah, it should be the LUB. No,
oh, right. Yeah. Sorry.
it should be the.
Yeah. Yes. That is correct. It should be the LUB. Yeah. This is correct, right? Yeah. So this is not continuous, and this also violates linear iteration because if you start linear iteration, so again you'll start from the bottom. So you'll start from bottom here is a0, so you'll start from a0. So f of a0 is going to give you a1. F of a1 is going to give you a2. In general, you can just say that f to the k of a0 is just almost by definition it's going to give you ak, right? And we know that like this thing will like if you take this basically
Once again,
right.
Gurban.
If you take this, then this will basically become this, which is as we saw 1, right? But we know that the lowest fixed point, actually the function has only got one fixed point, right? And that fixed point is 2. This is the only fixed point, so this is the least fixed point, right? So linear iteration is giving us a wrong answer in this case. So this is a fairly contrived example in the sense that we took what linear iteration is supposed to do and just like killed it, right? Because here we have got only one sequence that is even there in our lattice, right? So there's only one place in our lattice where we have a sequence tending to something, and we just make sure that linear iteration doesn't work there, and that's it basically. So here we didn't even have to take it as reals. You could have just like just said that this is your lattice and this is what your greatest this is what your meets and joins and greatest lower bounds and upper bounds are. And
yeah, but your lattice has to have kind of it has to be an infinite chain. See, because if it is finite, yes, then that itself will become the limit is always the fixed point.
Okay? Right. So it has to be an infinite chain. So
it has to be infinite chain.
Yeah. So this is one way of visualizing this in some senses, basically what I'm saying. But I think if you're talking about real-to-real functions, then there is another example, which is this. Let's say that our lattice this time is going to be 0, 1. Sorry. And we're going to also take something like 2, 3, right? So here the bottom is 0, top is 3. This is a complete lattice because all of these are closed intervals and this is compact, right? So now what we can do is basically we can say that essentially, if you look at it as a picture, what we can say is we can set f to be anything that basically slowly approaches. Okay, I think.
No, here I didn't understand the lattice. Is you're saying that what are the elements of the lattice? Any number. any number between, oh, it has any number
between 0, 1 and in between 2 and 3. But it doesn't have anything between
numbers.
1 and 2.
Intervals themselves are not the elements of the domain.
No. Yeah. So anything in this part, this and this is the lattice, right? Where this is 0, 1, 2, 3. And what we're going to do is, I'm just going to I'm not going to write out an exact equation for this, but you can just think of many different ways of defining this sort of a function. But I'm just going to argue just draw something visually right here. So you imagine that there's going to be one diagonal line over here, right? So this is your y is equal to x sort of a line here. What we do is, in this part of this lattice, we make sure that our function is going to be bigger than that. So something like some function over here. So maybe something like root x will actually work for this. So root x itself will give you something like this, but we keep a hole over here, right? And then what we do is, at 1, we send the value at 1 to 2 essentially. So this is going to be 1, and then you have 2 somewhere over here, and we say that, okay, the function is starting from 2 over here, right? So the file value at 1 is 2, and then at 2 to 3, let it just be constant 2, right? So then basically, if you can define it as root x, if it is x is less than 1, otherwise it is just 2, right? Now notice that if you do cleaning, okay, so firstly, what is the fixed point? So notice that the fixed point is basically just going to be all of these, right? And the lowest fixed point is going to be over here. Nothing below it is a fixed point, right? Because okay, so maybe we should not start from here. Maybe let's not take root x. Let's take something like something linear. Sorry. Basically, let's take half plus x by 2, right? Yeah, that'll work. So notice that anything less than here doesn't intersect the y is equal to x line. So anything in this part over here, nothing over here is ever going to be a fixed point. This is not a fixed point. So the only fixed point is going to be there, and those are the least fixed points, right? So now let's think about what will happen if you do clean iteration. So you start with bottom. Bottom is 0. So then if you apply f on it, f bottom is going to be your basically 0 plus 1 by 2. So it's going to be half. F squared bottom is going to be half plus 1 by 2. So it's going to basically become half plus 1 by 2, which is 3/4, right? In general, you'll find here that f to the n bottom will become 2 to the n minus 1 by 2 to the n, right? And this thing actually will tend to 1. So you get f to the n bottom. Sorry, again, I'm making this mistake. This is actually going to be 1, right? But we know that 1 is not a fixed point here, right? And this is again because of the discontinuity over here. Again, this particular sequence, any sequence here that you would take that will tend to 1, that sequence itself will go to 1, but f of that sequence will go to 2, right? Sorry, so f of that sequence will go to 1, but f of the limit will go to 2. So if you have any an going to 1, so you'll have this is equal to 1, this is equal to 1, but this is equal to 2, right? So this is not continuous and clean is violated again. Is this example clear? Does this did I mess it up and confuse you guys?
Drew has some question.
Okay, I don't have to chat in front of me. Wait.
That was a while back.
I'm sorry. Can you? Okay. Is it not relevant or did it get answered? Or?
Not relevant. something like
By
Huh?
definition, an infinite chain. What is it's by definition infinite chain? Assuming this is when n goes
well,
to
it's something that sir said that the chain needs to be an infinite chain in the
yeah.
previous
If you
example.
look, yes.
But
Yeah, but
Observation. See the definition of continuity. It has to preserve bounds on every chain. Okay.
yeah, I'm saying by definition the chain was an infinite chain, right? Because he said that en tends to
the
1.
preservation. No. By definition, the continuity, as Clay's theorem defines, is the bounds have to be preserved on all finite and infinite chains. Okay. But all these examples, are these discontinuity, etc., are only relevant in on infinite chains, because, as I told you, that monotonicity will automatically guarantee continuity. Okay, it will
No,
preserve bounds. Yeah.
yeah, and if I also, if I just may say something, if I understand what you're saying, so this, for example, is an infinite chain, right? Is this, am I getting at the right thing here? Like, it's an infinite sequence, but it's got only 2 elements in it. Is that the question that you're having, Dhruv?
Are you writing anything on the board? Because
Yeah. Here.
oh, I see. Okay. Well, technically, yeah, it's an infinite chain. Yes.
Right, and I think that, like, the fact that your actual elements of the chain forms an infinite set is not used in the proof. So I don't know if they really meant that or not.
Now I'm confused. What do you mean? Okay.
No, I think what Dhruv was saying was that,
No,
like,
so
yeah.
yeah, so what I'm saying is, like, in this chain, for example, there are AIs which are equal and the chain is also reaching 1, right?
In this
Approaching
case,
1
it's an
in
infinite chain. Yes. But when you say
Yeah,
by
so-
definition, it is infinite, what definition are you talking about?
well, it says that an tends to 1, right? For a finite chain, it does not mean anything to say the something tends to 1, because either
That
it
is
does
right. So these
equal
here,
1.
these examples are talking about infinite chains. Yes. Okay. But if you're saying, does the definition of continuity requires that all chains have to be infinite?
Not the definition of
No.
continuity.
No,
just the
because
fact
you
that
had in your
an
comments, it is by definition an infinite chain. That's what.
Yeah.
These
So what I
examples,
said was it is by definition an infinite chain.
what is by
which-
definition an infinite
Yeah,
chain?
just hear me out. I'm saying by so when you define that an tends to 1, then implicitly it means that the chain is an infinite chain, right?
Here it is infinite. Yes, all his examples here are infinite chains. Correct.
Yeah. So there was this comment by you, or maybe a question by you. I just wanted to clarify that it is by definition an infinite chain. So actually, it's out of context right now.
Yeah, I mean, in all these examples that Digantha is illustrating, and where violations of continuity, we are working on functions over reals with infinite chains. Yes. Because what we're trying to do is to find a violation to Clay's theorem, and that can happen only in the case of infinite domains. Okay,
Right.
because as I told you, by definition, it is the case that for finite domains, monotonicity of function implies continuity. Okay, because the chains, ascending chains, eventually have to terminate. Correct? There's no infinite chains there. And so, the limit of any all monotonic functions preserve.
So there is another. So is this? If
There
this
is a
okay?
Chandradeep's question.
Yeah. So does this work for all discontinuous real functions, and is as in when the domain is R, or the two different?
No, wait a minute. What does this means? What does this? As in when the domain is R, or the two definitions of discontinuity the same?
So, right. Yeah, I think that the definition of continuity in this sense is actually the same as the definition of continuity in the limit sense, and you can show that. I mean, this is, see, this thing is basically just supremum of image of whatever sequence you've taken, right?
Yeah, I mean, sorry for interrupting. So what does he mean by, what is the other definition? I, in the class, have a definition, okay, which is for every ascending chain, f of the limit, the upper bound of that ascending chain, these ascending chains could be finite or infinite, f applied to the least upper bound of any infinite chain should be equal to the upper bound of the chain that you get by applying f to individual elements. Okay, that is the definition of continuity. So is your question the same as the calculus one? Okay.
Yeah, I think it will be the same, because one of the definitions in the calculus side that we have is this thing, right? Like if you have an tends to b, f an should tend to b, right? Now, if you have an tends to b, then this is actually equivalent to having, like, you can, there's some case bashing involved, but I think you can reduce it to cases of this form where an is less than b, right? And then saying an tends to b is the same as saying this is b, right? And sorry, f of b. And then you can substitute that back into here and get the definition. I think if you follow something like this, you'll find that those two definitions are the same. I've not worked out the details. There might be something else going on there, but I think they're the same. Is that okay?
Yeah, I think so. I think it's right.
Right.
One related question. I mean, I already asked that question in the last class, but I want to ask again. Obviously, this is important. The continuity definition, as you saw, it is important for clearness theorem. Otherwise, clearness theorem fails. Okay, which is computing the least fixed point as a clean iteration of this collecting function. Why does Tarski's theorem does not require continuity? Can anyone explain? Tarski's theorem also has a characterization of fixed point that makes no assumption about that doesn't require f to be continuous. It characterizes characterizes fixed points for all functions. Does not require. Why? For all monotonic functions.
In Tarski's theorem, we are not just iterating over one element, right?
Yeah, but how are you doing it then?
I mean, we just define it as the greatest lower bound of set. So that is
not exactly set. Okay, it is, yes, of a set of elements, but set of elements that appear on any ascending or descending chains. Okay, or is the greatest lower bound of all elements that appear, the set of all elements that appear on all descending chains. Okay, so that's why it looks at all descending chains. So and as you can see, if it looks at all descending chains, it doesn't matter. Okay, so it's, yeah, I mean, you're right. Who's this? Chandradeep? Who's it?
Siddhant.
Okay, because I mean, this is one infinite chain, but you can also, there's also this this self loop at 2 in this example that Digant has shown. That's also an ascending chain. So it looks at both of them. I mean, as a matter of fact, yeah. So it ends up collecting all in that set, reductive and extensive sets, elements, all elements that appear on all the chains. Okay. And then collectively, it is looking at the greatest lower bound of the reductive set or the least upper bound. So in that sense, if you for these examples that Diganta has shown, why don't you try applying the Tarski's characterization for the same things, okay, by looking at computing the sets. Then you will see why it works, okay. So there it'll work, okay. It'll work in the sense the least fixed point, you get the least fixed point as the greatest lower bound. I mean, specifically, you see, this does not have a fixed point on the left side. So it has to look at this chain, okay, which is the self loop, and therefore it gets 2. Okay. And because that will be the greatest lower bound, correct? Of all, I'm sorry, that's the least upper bound of all descending chains. Okay, and this is also an ascending chain, and therefore that it gets. Am I right? Yeah. So because this chain does not include any fixed point, okay, and the least upper bound of all the elements that appear on all the chains is actually 2, okay, in that example that Diganta has shown, and therefore 2 will become the thing, and 2 is, that's the only descending chain anyway in this case. Okay, so 2 is also the least fixed point, and it's also the greatest fixed point. Okay. Yeah. The point is, it puts in that set, reductive and extensive sets, elements on all chains, and then takes the greatest and the lower bound. And that's why it does.
Yeah. So something like a chain like this is also considered.
Yeah, something like that is also considered, and it includes the elements of all of them. Okay, this is also a chain. Okay,
yeah.
The other one is also a chain, the one on which there is no fixed point. Okay,
right. Yeah.
So, and this one is greater than that anyway, right? 2. Therefore, it picks 2. Yeah.
Yeah. So the interesting thing is, if you had started linear iteration from over here, then we would have gotten it. So maybe there is some analogous thing that we can say that even if it's not continuous, we can, if there is some point from which we can start a clean iteration and get to the.
Yeah, but that also may not work all the time. Okay, it is true that cleaning situation, it can get all the. I mean, if it is continuous, it can get all fixed points by starting with different initial thing. Okay, that is always the case. Yeah. But in this case, it so happens that, but it is violating the fact that it is bottom, okay? Because that's also important. Because if you want to,
Yeah, from a verification perspective, it's important.
Yeah, I mean, all these things, by the way, I mean, guys, I mean, the reason that we're spending so much time on that, on this thing, is because this is a computational way of doing, getting the fixed points. And, and why are we? I mean, if the violation is only, if you only care about software verification, where you don't care about infinite state systems, etc. But it is still, this theory is applicable to infinite state systems. Okay, so you can have programs that manipulate reals and things and so on, and it actually works. The theory works for those infinite state systems as well, and you can actually compute these fixed points computationally, although it may not terminate all the time, because the clean iteration may not terminate on infinite state systems, but they can end up terminating in certain cases where the fixed point that if your transition system is such and is such that the fixed points that the inductive invariance that you want to compute happen to be the limit of finite ascending chains. Although the domain might be infinite, still the fixed points or the inductive invariance could be limits of finite chains, because you can have finite symbolic representation of infinite sets, of infinite set of reachable states. So it can work. This theory can work under certain conditions, and you can compute fixed points on infinite state systems as well. And that's why it is important to worry about. To understand this theory. Although on all finite cases, you automatically get continuity, and clean-ace iteration can be used.
Okay, so are there any questions regarding any of this, or should I move on to FramaC now? So do you want to say
No,
something?
I have nothing to add. Yeah.
Okay. I guess I'll move on to FramaC. So let me just save this. Save it later on. Yeah. So okay, let me actually, before I do this, let me actually quickly make sure that yes. Okay. So you guys will be able to see things actually. Okay, so let's look at FramaC. So before, I'll open up this tool. What is FramaC in some sense, right? So FramaC, also I don't know if I'm pronouncing this correctly. It's FramaC. Could be Frama or Frama, I'm not sure, but FramaC is essentially.
Is it Pharma or Frama?
Frama. Yeah, it's like Frama. I think it'll probably be either Frama or Frama. I don't know which one, but the tool is called Frama.
By the way, so this is a framework. Maybe we
we'll
do that introduction.
Yeah. So this is a framework for verifying a number, like for various different approaches of verifying C programs. It's meant for C programs. It is somewhat GUI oriented as opposed to CLI oriented. There is also very good batch mode, but I think some of these features that are there in the GUI, the CLI corresponding version is not really that great. And it's got a number of plugins, right? So each plugin is basically corresponds to one method of analysis of programs in some sense. And these plugins can talk to each other, right? So the plugin we are going to look at is called this evolved value analysis, or EVA essentially. And this plugin, basically what it does is that it'll do the thing that Sir described that all abstract interpretation systems is supposed to do. So given a certain program, say you have some program like this, say x is equal to some input, right? And then you say x plus equal to 1 and so on, right? It will basically try to compute some ranges. Maybe in some cases it might decide
before
that.
You get into eval, I think see, only one comment I want to make.
Yeah.
So it's a framework in the sense it has a lot of other plugins. The different kinds of analysis, like core logic, okay, trying to get strongest post condition, right, weakest precondition, that is also supported. Okay, so you could, there are plugins, I think, to do that, and you can make Hoare proofs also in this. Now, whether it supports model checking, bounded model checking in particular, I don't know about that.
No, I don't think it does.
Maybe it does, but yeah. So, like Diganta said, that today, he'll be concentrating on this EVA tool, which is static analysis by abstract interpretation.
Right. So basically, the idea with abstract interpretation is that you somehow come up with ranges. Let's just talk about ranges for now. Although There might be other sort of representations that you can have, when we look at them as we see them, right? So you can come up with certain ranges that for all the values in your program at each point, right? And then from these ranges, you can determine whether the program is safe according to certain things, right? So for example, if you're doing an x plus equal to 1, one of the things that can go wrong over here is an overflow that can happen, right? So if you know that the range of value from this input, say, is for some reason -10 to 10, then you know that, okay, this will not overflow given a 32-bit integer, right? So you can, from this range, you can deduce the safety with respect to certain properties. Okay, so FramaC basically does this. It will take all your variables, it will look at all of the points in the program in which they occur, and it will compute these sort of ranges and like other sort of set representations of possible values of these variables, right? So a few things to keep in mind is that this is an over approximation, right? So that means that the range of variables, like the range of x here is from -10 to 10, but it might not, like, that there is no guarantee that A, this is a tight range, and B, for a particular sequence of steps or a particular situation in your program, it might not be within, like, it might not cover this entire range, right? It might be some smaller value in this range, right? So for example, if you, for some reason, if you had some other thing that was influencing your input, based on that, the value of that other variable, this might actually belong to a much smaller range, right? So we will look at some concrete examples of this in a moment, but this is over approximate.
Yes, if I may just state it slightly differently. So what it computes are, yes, it's an over approximation of the strongest statement that you can make about the ranges itself. Okay, so these ranges include some unreachable. Okay, it include all the actual reachable values that x can ever take at that point, but it may include some unreachable things as well. Okay, that's why it is an over approximation. So it is, yes, it is in that sense an inductive invariant that includes, it's an inductive invariant, it includes all the reachable values that you can ever get to at that point, but some more. Okay, so we saw examples of this kind. Okay, for loops, so at loop x, we had I less than or equal to 2. I mean, they were strong inductive invariants, they were weak inductive invariants. So in that sense, it is an over approximation.
Right, and in fact, I think there was something in the assignment as well. So this computes over approximations, and the idea is that the consequence of that, one of the things that you should keep in mind is if it gives you an error, that means that may or may not be actually wrong.
So if it gives you an error of a particular safety property based on these inductive over approximations, I mean the invariants, then it may not. Just like it happened in the case of loops also. If you proposed an inductive invariant which was too weak for a particular property, just because the exit condition violated doesn't mean that the program is actually incorrect.
Yeah. So, and similarly, if there are no errors, then that means that the program is guaranteed to be correct, right? Because all of the possible values that x can take are guaranteed to lie within this thing. And if we know that all of the error or bad values are outside, then we know we have, in some sense, proven safety. So this is basically the idea with EVA. So it does this. So now there are some technical sort of specifications for any sort of abstract interpretation tool in terms of, okay, can it just do ranges or can it do other things than things other than ranges? What is what does it mean when it says that, okay, it's a value set of values and such things? I'll not just give you a dump of that right now, because that won't be too intuitive, but I'll just instead maybe show you as and when we see these things via some examples. So I'll just go directly to code examples right now if there is nothing that, if there are no questions and if anyone doesn't want to ask something or say something. Questions or comments? Okay, I guess I'll just go directly to examples. Yeah. So okay, before I talk about examples, I want to talk about, so I want to talk about the installation of this thing. Right. I have this document which I'll upload, and this install actually, initially I installed it via my own systems package manager, and that was very smooth. And that, while that worked, what they say to do officially is to install it via OCaml's package manager, which is OPAM. And I think that is the only platform independent way of installing this thing. So there are a few sort of things that you'll may need to work around, and some tweaks to their methods that I had to do. Like I couldn't just directly follow their methods on the website to get it installed. I had to do some of my own changes. One of those things is that they mentioned a package, but I learned that that package has been renamed. Things like that. Some dependencies didn't get installed automatically, so I had to do some of these things. So I've talked about that in this document, and I also talked about some of the things that I think that you might have to go through to install it on your system. But basically I feel that the installation of this will probably be somewhat different for each one of you, given your specific systems. So I would like say that just get it installed, because it might take some while to iron out the install process. Let's get started on getting it installed. There will probably be something that you may have to do, like work with this, so maybe just try and get it installed. Yeah, but basically you can try and get it installed via the OCaml package manager. Okay, so
Can you please share this?
Yeah, I will definitely. Yeah. I actually thought that initially I'll go through some of this in the tutorial, but then I thought that that'll probably just be, I don't have that much time right now. So okay, so this is the first example. This is a very simple example. What we're doing is we are taking some input x, and then we are dividing it by 2, and then adding 1 to it, and then we're printing out the value of x again, right? So when you install FramaC, you'll get two things. You'll get this FramaC CLI, so you can do a version of that, and this will basically be your command line tool that you use in batch mode. We'll not be using this. I mean, I'll at least not be demoing this at all. What I'll be demoing is the GUI version. This is called the FramaC GUI, right? Can you see the terminal down here?
Yeah.
Yeah, okay. So it's a FramaC GUI, right? And the way you call it is you just, you want to do the EVA, right? So if you want to call it with the EVA plugin, you do -EVA, because there are other plugins as well. So if you don't pass which plugin it'll like not really initialize anything. And then you pass it the name of the C program. So in our case, it is linear.c. And you can pass in multiple source files at this stage as well. It'll load all of them together, and it'll also automatically go through, say, files that you have included, and load them into its analysis as well. So it's actually good for code exploration and things like that as well, and we'll see. So yeah, so this is what you do, and you run it, and it'll load up. And let me just make it big, right? So is the font size okay? Can you see the text on the GUI thing?
Yeah, I can see it. So I'm sure that everybody else can.
Okay. Yeah.
Old man's eyes see it.
So yeah, so I have, in some sense, figured out how to actually increase the font size finally. It turns out that you have to do it on your own system settings. You can't do it inside FramaC anywhere. Yeah, so in any case, let's look at this thing. So on this side, you see the actual program that we have loaded in. This is a C program. So the first thing that FramaC will do is basically convert this C program into its own internal representation, which is the representation called the go-to program, right? It is very close to C, except that it uses some go-to functions and like go-to statements and things like that.
Yeah, by the way, CBMC also uses go-to as this go-to programs as internal functions. And actually in CBMC, I mean, here also it's displaying. In CBMC also, you can get it to put out the code.
Yeah. I think there is an intermediate file that you can get out of it also. Yeah. Sorry for. Hello, am I still audible?
Yeah.
Yeah. So this is the go-to program. So now basically, first things that you would want to do is basically, if you go to any line over here and highlight it, the relevant tabs on the bottom will show you some information with respect to that, and that information would be related to whatever plugin you're running. So over here on this side, you can see the mouse, right?
Yes.
Yeah. Okay. So over here we have various different plugins that you can run, but we're looking at EVA right now, and it has already been run. You don't need to click at run again, but you can if you want to. So if you look at any of these parts of your code, it will give you some information regarding that, right? It will give you what this function is. There is some instantiation that it does for variadic functions and stuff like that that it is showing you over here. And then you have your return value and such things. So the main or the sort of most important part of EVA, or when you're using EVA, is two things. Firstly, you look at the messages tab, right? So the messages tab will usually have any errors that EVA has detected. Like it will show you that EVA has detected an errors. Right now, messages tab is empty, which means EVA has not detected an error. So what does that actually mean precisely, right? So EVA has its own internal list of possible errors that it will check. Things like overflow, underflow, out of bounds, like pointer accesses, dealing with uninitialized values and such things. And you can experiment with all of these errors and see what EVA does with them, right? So there is this internal list of errors that EVA can handle in some sense, and EVA can check all of those things. And messages being 0 means that none of these errors have been detected, right? So that means that none of these errors are happening in your program. That means that EVA has actually been able to, via these bounds or interval propagation and analysis, it has been able to prove that no such error is happening, right? The next thing that you would want to look at is this values tab over here. This will actually show you these ranges of values that EVA has calculated. So if we go to this one over here, so now we are selecting X over here, right? So we are saying what is the value of X at this statement, right? So you see that you have got two columns over here. One is this X and one is X after, right? So X is just the value of the variable before the statement was executed and then after the statement was executed, right? So you notice that the value before was uninitialized, and then the value after is this entire range of int, right? Minus max int, like min int to max int essentially. So notice that uninitialized is this one special value that EVA assigns, right? So EVA actually makes a distinction between something being just a random, some value in which is an integer, which is what this is saying, right? This is some integer versus an uninitialized integer. So EVA actually deals or treats uninitialized values as special things, and the motivation for that comes from security analysis essentially, because you can in some sense influence these uninitialized values in security critical systems to compromise them, right? So EVA will raise special errors if you're using uninitialized values in your calculations, because a priori if you use X in a calculation and that X is just some integer, that is not necessarily an error. But if it's an uninitialized integer, then that is an error. So EVA needs to make a distinction. So X before is considered to be an uninitialized, and after EVA just says that it's something in this range, right? So now let's go to the next statement. So in the next statement, we again see what X is, right? So X before was the whole min into max int. Now EVA actually finds out that the interval has shrunk. It's min int by 2 to max int by 2, right? Then we do X plus plus, and again, the entire interval shifts to the to the positive side by 1, right? So you got 4 here and 3 here and so on. So this has shifted to the 1, right? So your interval has been propagated like that. And finally, that is the range of values when you're printing it. right? So just a quick tour of the GUI I wanted to give with this example and some of the things that are going on. So here you have your files and your potentially multiple functions inside each file. If you look at it, Eva is also loaded in things like library files, which we'll not look at because we don't need to. But in general, if you think that if you have a really huge code base, then you'll have all your files over here and you can explore. Here is where you get various options for Eva. You can also access more options from over here. You have got things like some options that we'll not really get into at all over here, but these are there in the GUI. The main thing is these two windows. This is your original code, which we already have over here. So I'm just going to shift it like this. And then the go-to program, and then you have got your values here and messages here, right? So any question about anything so far? No? Okay. So now let me go to the next one. So the next one is going to be this particular file called linear2, right? And let me load up the actual program over here. So yeah, now in linear2, what we're doing is we're doing the same thing as we were doing before, and now we're doing x star equal to 2, right? So can anyone tell me, is there an error that will happen here, and if so, what? I mean, I have Eva right there, but like before we go there, am I still audible? Yeah.
X is uninitialized, right? So
yeah, but that will not throw an error. See, if that were to throw an error, that would throw an error here as well, right? Here we see that didn't throw an error. Scanf can safely take uninitialized.
Oh yeah. Sorry.
Right? Yeah. So X becomes initialized after scanf, so that is not the issue. I mean, if this were to throw an error, there's only one extra statement here, which is this one, and the error has to be over here, right? Like, I mean, just in terms of the previous one didn't have an error. So yeah, so basically, let's look at what Eva will tell us.
Signed overflow.
Yes, exactly. So it gives us a message, right? Signed overflow. And it says this thing, right? So now look that in this go-to program, Eva has added this. There's a few things that happen. So firstly, there's a message for the signed overflow error that Eva thinks might have happened. But like I said, when Eva says that there is an error, the error may or may not have actually happened, right? So what Eva does is that Eva actually adds an annotation which will assert the condition that needs to be checked at this point. So Eva realizes that the interval analysis doesn't, eliminate the possibility of a signed overflow in this statement. So it adds an assertion to check that signed overflow at this point. Now Eva itself cannot check this assertion, but there are other, plugins here which we'll not look at that can do things with this assertion, which is why this is here, right? So now if you go into the values tab, you'll again see that if you look at the value over here, X before is this and X after is this, right? And you have a signed overflow. So now let's actually, okay, so let's see why the signed overflow is happening, right? Because you've got 2, 4 over here, 1, 0, like this, max sinned by 2 plus 1. And then if you multiply that times like 2, then you'll get an overflow, which is why the overflow is happening, right? So now let's actually look at a few things that is also going on over here, right? So notice that if you go to this particular thing, the after here has got this weird thing in it, right? It shows you, even though there's an overflow, it shows you a range of values that will happen after this, right? So this range that it shows is basically the range of values that X will contain if no error happens. So the actual set of states at this point for X is in some sense this range and an error state, which corresponds to the signed overflow state, right? So you have a range of things over here and an error here, right? So that is your situation at this point of the program.
That's because as per C semantics, it does kind of wrap around. Okay?
Yeah.
That's why it is still within this range. But that's why it is having one extra, right? So this is, yeah. It is
Yeah.
a-
So in terms of the wraparound, I don't know if this is the exact force condition that will take up if it is wrapping around, but it actually
No,
is.
signed overflow is undefined behavior. Unsigned overflow wraps around.
Okay. Right. But I think if you were to implement this in most compilers, it will actually still wrap around or something, right? Like it'll do a garbled sort of wraparound to the negative side, right? Hello?
Yeah, I don't know what
Yes, it
exactly.
generally does.
I think it wraps around is what I feel. Okay. In ANSI C also it wraps around.
Yeah, I think but like just I don't know, but like I think the strictly the standard might not say that like that is defined, which is why it saves as an error. But I think if you were to actually run this, you would get a wraparound in most compilers.
Right. Yeah.
Yeah. So that is one thing. So you get some set of values over here, and you have an error state corresponding to this. So by the way, this red like square over here, this is what is telling you that you have an error at this point. Now, the other thing that I want to sort of point out in this particular example is that the set of states here has got this weird 0% 2, right? What does that mean? So you see, if you multiply x by 2, the set of states that you'll get is not just going to be your plain range, right? So it's going to be, of course, something between something within some particular range, but more than that, it's only going to be even numbers within that range, right? So EVA can actually make your value, like the domain or the set of values that you're using, the representation of the set of values, it can actually also say things like, okay, the variable can be anything in this range, which is something mod something, right? So in this case, it's saying it's anything in this range, which is also even, like 0 mod 2. So EVA can say things like that as well. So as we'll go forward, we'll see more and more sort of
yeah. So you already seen two things. I think it is using both. You've already seen a simple interval domain.
Yeah.
As well as this, what is called, this is usually called a congruence domain. I think this is congruence domain that it is using. I think on the interval domain, it kind of it usually uses an interval domain which is, it collects larger than the actual value that can be stored in a particular length of bit vector, and that's why it is able to get that if you allowed one extra bit, then it can actually, the value can get to this blah 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 647, which is an overflow. And that's why it does that.
No, yeah. So I think this particular range is actually within the representable range. I think it just like drops the values that would have led to the overflow. So it's like so in some sense it's basically like this. So if you had I think this is what's going on. So if you had like say this is your values in the pre, and then some overflow happens, then say you have got the exact set of values would have been something like this, but the representable set of values is this.
Yeah.
So I think what EVA returns is an over approximation of the representable set of values, and just something saying error. So I think this is what EVA is producing for that. So this is actually
and I think the capability to produce an error requires you to have this that it can potentially yield.
Yeah, definitely. Yeah, I think definitely.
Some of these analysis we will see. Okay, when we in the regular lectures. Okay, so as to how it computes the inductive invariance and so on. Yeah, go ahead. Yeah.
In fact, yeah. While EVA had an issue with one of the OCaml big number libraries, so I think it definitely uses this sort of big num representation somewhere. But yeah, in any case, so this is the domain or the range of values after this. Okay, so it is this congruence domain, and it is basically the representable set of values and what particular error state, right? So the other
how should you, can you explain, Diganta, how should, I don't know if people, I mean, I'm a little bit confused here.
Yeah. Hello. Hello. Hello.
Yeah, you're audible.
Did you guys catch what I was asking?
No,
Or,
no.
okay. Hello. I think. Okay, I guess. I think sir's net is probably. I think I'll just say continue to say things. Right. So the third thing that I want to sort of point out over here is that if you look at the set of values here, notice that this is basically the it corresponds to this green range of value that we over here, right? This over approximation of the representable set of values that you had. So that is the error-free set of values, right? So in some sense, the exact the exact set of values that you may have will be divisioned into two parts. One is error-free, and the other one is errored. And I think it actually over approximates the error-free as the range of values at that particular point. And it just says that for all the other values, it just says that, okay, those values will just cause an error, right? And it will only show you the error message in the statement where it occurs first. So there is only an error message here. Although, technically speaking, if you were to say propagate this error value forward, you would get an error message here. That it does not show because I think because otherwise it'll just flood the logs with, and overflow happens here. You're dealing with an overflow value here. You're dealing with a value count that comes from an overflow over there, and so on, right? So I think it basically drops all of those values that will potentially come from an error situation and then propagates the error-free things forward, right? So is this clear so far? Any questions?
Can you go back to the line above this?
Right. This one you think?
Yeah.
I think
Hi, sir. Yeah.
My internet went off. Okay.
Yeah.
What is the second bracket 2?
Oh, right. Yeah. So
yeah.
So basically, this will show you all the values of your sub expressions. It's just saying that the value of the sub expression, which is a constant 2, is just the single constant 2. Right? It's just talking about this one. Is that clear?
Yeah. What exactly? Multiplied by 2. That's what it means. X. It is assigned.
Yeah, X is being multiplied by 2 and then put into X again.
2 times X. Okay, is what is being assigned. So what does So this also not only gives the range, but also says it's even. Okay?
Yes. That is the. That is the It's a really. I mean, the representability is really nice, I think.
Yeah. Hey, by the way, I don't know. I mean, what's your normal practice? Because you.
Right. I at some point I think I go no further than 6:30 usually. So by the way, the guys, are you okay with 6:30? Or should I stop before that? Because I can just continue this next time or something.
Yeah,
right?
I mean, but you can stop it. I mean, if you put them in a spot like that, they will. I mean, if I put them in a spot, usually they'll probably not. Maybe.
No. I mean, see, this is okay. So just to not put anyone in a spot, basically, this is all optional. So I'll only go as long as you have time. I can sit here and keep talking for as long as you want me to.
Oh, there's someone has commented assignment. Okay, so they still have to finish up.
Oh, right. Yeah, fair enough. Yeah.
So 6:15. So why don't you go to 6:15?
Yeah, so Chandra is 6:15. Okay, also I'll just finish this linear set of examples and stop, right? Right.
Oh, you have a conditional example?
Right. Actually, you know what? Let me just go to there. So I just want to quickly show this next one. This is the yeah. Let's skip this one. Let's go to the linear guard one. So here I've actually eliminated the overflow condition by putting a guard over here. I just want to show that Eva actually recognizes this fact. Oh, and it's not star equal to x. It will be star equal to 2. So, right. So this in this code, we just check that x is in the -100 to 100 range, and if it's not, we just exit with a message saying it's too big, right? So you're only dealing with inputs between 100 and like -100 and 100. Okay, not inputs, but like values of x after this point between -100 and 100. So let's go to the intervals that we have for this one. So initially, again, you have, okay, so let's go to the values thing. So firstly, messages is 0, right? Which means that Eva has found that no potential for error in this code, right? Which means there's no potential for error in the code. So let's go to the values thing. Here the values is between, the entire integer range in scanf as usual. At x by equal to 2, it's again half of that range, and then we again shift it by 1 as we were doing, right? So now if we go to this statement, so this statement, you see, Eva says that it can be either 0 or 1, right? Because x can either be less than 100 or greater than 100. And now then there's this complicated go-to statement, but it basically just this entire this pair of go-to is just saying or essentially. But the else part is again something like that. It says that, okay, x can be greater than 100 or not greater than 100. And then, inside we just say return -1, right? But notice that after all of this, when we go to this point, Eva actually realizes the value of x is between -100 to 100, right? So because we have eliminated the case that x is less than 100 and eliminated the case that x is greater than 100, Eva realizes that the value of x before this statement, right before this statement over here, x star equal to 2, has to be from -100 to 100. And then, like before, after the x star equal to 2, it says that the value would be -200 to 200, and it has to be even. And it doesn't produce any overflow at this point because, of course, like 100 to 100 is a very representable range, So yeah, is this example okay? Is this clear for everyone? So give me a yes, please, someone.
Yes.
Okay, thanks. All right, so this is fine.
Yeah, I mean, go back to that. I just want to point out, make one remark. Okay, go back to your previous. I don't know if you want to get.
Yeah. This is the one.
So there is something. So for example, yes, it does. It has to take a kind of in this case.
Yeah, I have a better example for that.
Okay.
The join, I have a few better examples for that.
Okay.
So yeah, so if you give me I'll just go over those examples because I think it will be easier that way. So yeah, so let me just look at this example now. This is basically the join that Sir was talking about. So so let me just go over this in this editor itself. So we are inputting some x, and then if x is less than 0, we are setting y to be -1, and otherwise we're setting y to be 1. So essentially we're calculating the sign of x in the most direct way possible, and then we are outputting everything, right? So let's see. There is no potential for error here, of course, but let's still see what Eva has to say about the values of various things that is for this program. So this is branch.c, right? So again, when you input x is let's go to the values tab. So x is initially uninitialized, and then after you've inputted it, it can be anything within the integer range. Now y is of course uninitialized at this point. No value, because in this statement there is no expression being computed, and essentially y is uninitialized at this point. X may or may not be greater than 0, so that can happen. And then here what we see is that y was uninitialized, and we are setting y to be -1, right? So we know that at this point in the program, y is always going to be -1, right? Similarly, at this point of the program, we know that always y is going to be 1. So the question is, what's going to happen after this, right? Because now you have got two branches that are being merged essentially over here, right? So what's going to happen over here? So Eva will automatically take the union of whatever. So you'll have one domain of values for y over here and one domain of values of y over here. And Eva is going to take the union of those two things and set that as the range of values after your branch has finished, right? So that is the join operation you're talking about, right, sir?
Correct.
So in this case, you see, Eva recognizes there's only one possible value of y in each one of these branches. So the output is actually like in the output statement, you get the range of values for y to be just two values, right? So Eva will say that, yeah, okay, there's only two values of y that is possible here. It's either -1 or 1.
Yeah, see, this is smart here because it is switched over to a different domain. If
Right.
it was consistently using, by the way, guys, if it was using an interval domain, then your join of those two interval domains will be -1 to 1, which will include a 0, okay, also in it, okay. I guess this here, this is not an interval domain. This is more a enumerated domain. Okay?
Yes.
So it can, if you use the enumerated domain, which says, okay, some set of finite values, that it, whether they're equal or not. Therefore, it's switched over to the enumerated domain and then said -1 and 1, because that's the most precise that it can say about, the strongest thing that it can say there. But if you had forced it to use an interval domain, then there would be a loss of precision there, because the join of those two interval domains would be -1 to 1, okay, and then which will include an unreachable value 0. So that is an over approximation. So if you had forced it to use an interval domain, it would have concluded deduced -1 to 1, which includes 0 also. Yeah. Okay, that's the point that I wanted to make.
Yeah.
So, but it is switching over here to a enumerated domain. Yeah.
So if you guys are curious about what are all of the possible sort of representations that Eva has for sets of states, these representations for sets of states are called domains, abstract domains. There is a list of these in the Eva's manual, which I link on Moodle. And they say what is for integers, what are all the domains it supports, and then somehow it intelligently picks one of them based on what your program is, basically. Yeah, we'll maybe see like some of that later.
Yeah.
Okay, so I think this is 6 20. Yeah. So yeah, should I do branch 2 and 3 and then
let's continue
later?
I don't know. I mean, yeah, it's better that you continue later on.
Yeah, I think that's true. Yes. So okay, I'll stop over here. Any questions so far? I'm going to just bring up the Eva. Any questions? Okay. So all right, then I guess that's it. So in any case, do you find this Eva to be in any sense do you find it surprising that you can actually calculate these values, or do you think that this is fairly trivial to do? Just curious what you feel about like.
You're asking me, or you're asking generally?
I'm asking everyone. Like I know that this is fairly involved, but I'm asking them whether they think that this is just propagating intervals, whether they think it's easy or not. Because
isn't CBMC kind of doing the same thing with SSAs and merging and all that?
No, that's yeah. So here's the thing, right? CBMC is not. So there's one very big difference, which is that CBMC is actually under approximate, right?
No. Okay, CBM. Okay, so there are two axes. Okay, yes and no is the way that I would answer.
Right, yeah.
Okay, CBMC is propagating. It is not doing any abstraction. I mean, it is not doing any abstraction of value. It is not using abstract domain. Okay, to be very careful. Yes, it is doing under approximation as far as loops are concerned. Okay,
right.
Now, so far we have not seen any loop programs. Okay, so for the programs that you have seen just now, okay, which are all loop-free programs, under approximations, does not come into picture, okay? Because the only under approximation happens in CBMC is with respect to loops. So we'll see how the loops are done in EVA, okay? Now, so if you only look at branch programs, CBMC does a lot more than this, okay?
Right, yeah.
So a lot more than this because it is propagating sets of values precisely as strongest post conditions, okay? So it'll actually get, in this example, if you're using interval domain, there would be a loss of precision, okay? Now, you lucked out in here that there was only two possible values here, so we were able to represent as -1 and 1, okay, as a finite set. Okay, now CBMC would be using predicates, yeah, predicates over numbers, and it can use any first order predicate, okay, quantify C. So in that sense, it propagates sets of values represented as predicates, which in a lot of cases is a lot more precise. Whereas here it does, it uses abstract domains and it's precise with respect to those abstract, it is an over approximation with respect to those abstract domains. So in that sense, CBMC is a lot more precise, okay, where it comes to, in terms of the domain of values that it is propagating. So here, certainly it is more abstract. And that's why it is a lot more efficient, significantly more efficient, and it trades off precision to accuracy, okay? So when it cannot, like in this case, if it uses interval domain, it can look at the max and min of the things. Okay, I think we are going beyond. Okay, these we will see later on, okay?
Yeah,
so
and also,
yeah,
go on, sir. Sorry.
Yeah. That's the point I was making. I'm trying to answer the question. Okay, doesn't CBMC do this? CBMC definitely does this. Okay, so if you had an assertion here saying that x is either equal to 1 or -1, it would have precisely analyzed that and then said yes. Okay, which is exactly what So in that sense, it is the same thing. So yeah, so it is more precise than that. But when you get to loops, you will see that bounded model checking is an under approximation because it does not compute inductive invariance over loops, whereas EVA does compute inductive invariance over loops, but in an abstract domain, okay? So in that sense, for loops, you will see if you look at the bounded model checking CBMC as opposed to EVA will be a lot more powerful. Okay.
Yeah, in fact, I think I'll try and show like one program and run it both through CBMC and EVA and see like what we see in both those cases.
Sure. Yeah.
Yeah. So okay. Any other sort of questions or comments? Other than that, I think it's acceptable. So I guess.
Okay. Thank you.
Okay. Thanks, everyone. Bye.
You were not recording, were you?
No, it was live on YouTube, right? So it'll be there on your playlist automatically.
I think so, but because something went, the current went off. So
Okay. Let me just view the stream on YouTube just to make sure that
maybe it is still live. So maybe I don't know if it.
Yeah, it was there. I think everything is.
Just in case it lost, then I wanted to.
Right. Yeah, that would have been a good idea maybe to record, but I think at least from what I see on YouTube, it's all there.
No. On YouTube, it may be there only for the few minutes. Okay, after the thing. Okay, whether the whole thing is there or not, I don't know.
Yeah, so I'm just looking at it right now, and it's some 1 hour 15 minutes long.
Okay.